We're going to look at the derivative of x cubed. And I do mean look. It's not just that we're going to find the answer, or not just a proof. We really want to see why it comes out the way it comes out. And the way we're going to do that is we're going to think of the derivative, of course, as the instantaneous rate of change. So what we want to do is visualize the instantaneous rate of change of x cubed. How are we going to do that? What we want is a physical representation of x cubed. I'm not talking about a graph. I'm talking about something from the real world, something we can really see and get our minds around. We want a physical representation of x cubed. What would that be? Well, we all know that the volume of a cube of side x is x cubed. So that volume of a cube is a physical representation of x cubed. I mean, of course, that's why we say x cubed sometimes rather than saying x to the third. So let's draw ourselves a cube. Here's a cube of side x. And the question is, what's the instantaneous rate of change? Whoa, you might say. What do you mean change? What's changing? It's just the cube. Well, to say it more completely, we want the instantaneous rate of change of the volume of the cube compared to a change in the side. So we've got to change the side by a little bit, see what happens to the volume. So we change the side by a little bit. There's 3 dimensions of the cube. They're all x. So we change it by that same little bit, delta x, in 3 different dimensions. And what happens to the volume? Well, you grow extra volume, right? The original cube is still in there. We've grown these 3 extra slabs on the cube by changing the side by a little bit. And look, this already is giving us the answer. When you change the side by a little bit, you get 3 slabs, and they all have sides x squared. And what that means is the derivative of x cubed, the rate of change, is 3x squared. Let's see that a little more slowly. Those 3 slabs, the change in the volume, 3 of them, 3 slabs, each one has dimension x times delta x, so their size in volume is x squared delta x. That's the actual change in the volume. We want the rate of change of the volume, so we divide by delta x, and that gives us 3x squared. The delta x cancels out. Finally, we take the limit as delta x approaches 0, and we get the derivative is exactly 3x squared. We're done. End of video. No, look, I know, that went too fast. We'll take it from the top. We'll go much more slowly. I'll give you all the details, but I wanted you to see the main point. The reason that the derivative of x cubed is what it is because that's how a cube works. If you grow the side by a little bit, you basically get 3 big pieces, and each of them has side x squared. And we'll now work our way towards that very slowly. So let's go back to the cube. All right, here's the cube of side x. And what we're saying is the volume is a physical representation of x cubed. We originally wanted to find the derivative of x cubed. That's the same as saying find the derivative of the volume with respect to x. What is that? What's the instantaneous rate of change of v relative to x? All right, so we're going to employ a strategy here. This strategy is going to be perfect for this case, and it works in most cases when you're trying to find the instantaneous rate of change. Before you find the instantaneous rate of change, the first thing you do is you find the rate of change itself. I think you're familiar with delta. I've used it several times in this video already. Delta is standard notation for meaning change. So we want to get the change in the volume in terms of the change in x. That's just the change itself. Once we have that, we can get the average rate of change by dividing delta v by delta x. And then once we have that, the third step is take the limit as delta x approaches 0. The average rate of change becomes the instantaneous rate of change. That's the volume. That's the thing we're interested in. Okay, so let's look at our cube here and grow it. We're going to grow the sides x by delta x. So that affects 3 dimensions, coming towards you, going upwards, going out to the right. So having this longer side means you have a bigger cube. I've just drawn the outline of it, the frame of it, in purple. So we have a bigger cube compared to this smaller cube we started off with, and we want to get the change in the volume. Now, it'll be profitable for us to break that change in volume up to several different pieces, so let's look at them one at a time. First, there's a piece coming out towards us, a big slab, and then there's another piece on the side, and then there's another piece like that on the top, and that's pretty much most of the volume. Well, there's a little bit extra here. You got these edges, so let's fill them in. There's 1 edge, 2 edges, 3 edges, and then finally there's a little piece up here. That's the corner. Now let's look back at our strategy. What do we want to do about this? We've divided the change in volume into 7 pieces here, the 3 slabs, the 3 edges, the corner. And the strategy says we want to get this change in volume in terms of the change in the side. So let's first write down that change in volume. Slabs, there are 3 of them. Edges, there are 3 of them. corner, there's one of them. Okay, so that's the total change in volume, but we want to get it in terms of delta x. So I'm going to just take the corner out for a second so we can see the dimensions a little better. How about the slabs? The slabs, it's a block, so the way you figure out the volume is the height times the width times the depth, x times delta x, that's the depth. So the volume of the slab is x times delta x, or x squared delta x. How about the edges? They each have a long dimension x and two short dimensions delta x, so the volume of an edge is x times delta x squared. Finally, the volume of the corner is missing, but you can see the dimensions, delta x, delta x, delta x. So I'll put the corner back in and change this to delta x cubed. So we've accomplished the first step. We now have the change in the volume in terms of the change in the side. Now, I need a little room here, so I'm going to have to erase this strategy statement, so let's just make sure we know what the next two steps are. We want to go from the actual change to the rate of change by dividing by delta x, and then we'll take the limit as delta x approaches 0. So let's make some space, divide delta v by delta x, and what do you get? There's three separate terms, right? You divide each of these terms by delta x. The first term you divide by delta x, that cancels the delta x out, so you have 3x squared, that's this. 3x delta x squared divided by delta x, there's still one delta x, so you have 3x delta x cubed divided by delta x, you get delta x squared. So now we've got the second step. This is the average rate of change, this expression. And what we want to do next is take the limit as delta x approaches 0. I need a little more room, so I erased that top part, and now I'll move this up to the top. All right, we're going to take the limit as delta x approaches 0, and what are we going to get? We get this. Why is that? The definition of the derivative is the limit of the average rate of change as delta x approaches 0. So here we get the derivative. 3x squared, not affected by delta x going to 0. It stays the same. And these last two terms, they have a delta x in them. The x is not changing. The delta x is going to 0. So they wind up being 0. 3x squared plus 0 plus 0, of course, that comes out to 3x squared. That's what we said before. The answer is going to be 3x squared. But I want you to see where these zeros come from. This is an important part of the whole thing. This 0, remember, this came from x times delta x times delta x. That was the volume of an edge. What we're saying here, the edges, because they have two dimensions of delta x, when we divide by delta x to get the average rate of change, it's still left with the delta x. So in the limit, it goes to 0. Same with the corner, which is even smaller. So the essence of all this is that the main part of the volume really is those three big slabs. So that goes back to the thing I said way in the beginning. The volume is pretty much this. It's the slabs. I mean, the cube is still in there. So when you change the side by a little bit, you get three big pieces. The change in the volume is these three pieces, each one of which has side x squared delta x. It's virtually that. That's why I'm using this approximately equal sign. We saw that the edges and the corner won't matter in the long run. So because this is pretty much 3x squared delta x, the rate of change, the average rate of change is 3x squared, and that means the derivative is 3x squared. The derivative of x cubed is 3x squared. And again, it's because that's the way a cube works. It's not magic. That's the way a cube works. When you expand the side by a little bit, the effect of that is you get three big pieces. They each have side x squared. The derivative of x cubed is 3x squared. Now, this is part of the theme I'm trying to show you in all these videos. Calculus makes sense. It's mostly based on things you already know. There are plenty of other videos for you to look at. One that you might want to see after this is the proof. There's an official proof that you'll see in almost every book. You take the definition of the derivative and you follow it through. It's a bunch of algebra. It doesn't seem to make a lot of sense, but in the video I'm going to show you, I will show you how that algebra relates to the 7 pieces that we created in the volume of the cube. So that proof will make sense. Another thing you can do, there's some other videos you can look at. The derivative of x squared, it's very much like this one, except we're using a square, not a cube. And this other one, the derivative of 1 over x is the same as x to the minus 1. Well, you might think, look at this, how are you going to get this crazy answer in a picture? But we can, and it's very useful, I think. You might want to take a look at that one.